Here's most of the review problems that we did in class on Friday, January 15th, 2021. I'm just going to go through them pretty quickly right here. So starting with 5.1, we have the natural log. So natural log of x, all these arrows I drew are going to indicate a derivative. So natural log of x's derivative is 1 over x. Now if instead of x, it's a u, some other function in there, we have to use chain rule. So that means that the derivative of natural log of u is 1 over, and instead of x, we keep whatever that function is. So that's like our inside function, we keep it safe. And then since it's chain rule, we have to multiply times u prime. Now, you could write that slightly differently because u prime is multiplied times this fraction. You can multiply u prime times 1, so u prime could be on top of the fraction. So either one of these is valid. Let's jump right into number 41. We've got the natural log of 3x. Now, this is not just natural log of x, you got a 3x in there, right? So that means that u is 3x, which means that u prime equals 3. So y prime is going to be 1 over u, which is 3x, times u prime, which is 3. And then we can rewrite this as 3 over 3x, which reduces to 1 over x. So it looks like if this is any kind of a linear function in here, we're going to end up with like a 1 over x kind of a situation, if it's like a one-term linear function. All right, most of the time though, it won't be just 1 over x. All right, number 47, natural log of t plus 1 squared. So in this case, t plus 1 is in the parentheses, and then that whole parentheses is squared. Okay. If this 3x was squared, we would be able to do the same step. But if it was just 3x and the x was squared, not the 3, we would not be able to do this thing that we're about to do. Okay. So since this is the natural log of the whole argument squared, we can rewrite this natural log using a log rule, log property that you learned back in like Algebra 2 probably. So that 2 exponent gets to move out to the front. So the original function equals 2 times the natural log of t plus 1. And now we can take our derivative. So I'm going to just bring that 2 down. Natural log, we're going to take the derivative, and t plus 1 is u, so that's going to be 1 over t plus 1 times the derivative of t plus 1, which is 1. And then we can do a little bit of cleanup. 2 and 1 are just normal numbers, so they'll get multiplied times our numerator. 2 times 1 is 2. And on bottom, t plus 1 sticks around. And we are done with that one. Okay, those problems were directly from your homework assignment in 5.1. The next couple of problems, this is similar to number 49. I just got rid of the product rule that was involved because I wanted to show you something specific from it. And then this is an example that shows up kind of a lot, natural log of x. So let's start with this guy. We've got natural log of the square root of x squared minus 1. So this is a double chain rule because we have 3 functions, natural log, square root, and x squared minus 1. We don't want to use chain rule twice if we can help it, so let's see how we can rewrite this. Often we rewrite radicals as something to the 1/2 power, and we just keep the inside exactly how it was. Okay. Now we can rewrite with the 1/2 out in the front. Guess I should have left another line, but this is going to equal 1/2 times the natural log of x squared minus 1. And now we can take the derivative, bring the 1/2 down, times 1 over u, u is x squared minus 1, times the derivative of x squared minus 1, which is 2x. And then we can clean this up a little bit. The 1/2 and the 2 are going to cancel each other out using multiplication. That x being a normal x will move up to the top, x over, keep x squared minus 1 on the bottom. Last guy here is natural log of x. We got a couple natural logs. I think it's easiest to rewrite this one as natural log of u, kind of like this, and then do some side work. For our side work, we are going to show what u is and what u prime is. So u is the natural log of x, which means u prime is just 1 over x. So that's just this piece right here, u and its derivative. But this is the inside function. The y prime is going to be 1 over u times u prime, right? Because this is just natural log of u. Y prime is 1 over u. U is natural log of x, so let's do a rewrite there. 1 over natural log of x times u prime. U prime is 1 over x. We can be done right now unless this is multiple choice, and it's totally possible that the multiple choice answers would rewrite this in a different way. It would probably not be rewritten like natural log of x times x, because it's hard to tell whether the x here is supposed to be in the argument with the other x. In this case, it is not. It's its own separate little entity. So you could do parentheses there, or you could put 1 over x times natural log of x, and that's probably the best way to write it. Moving on to e to the x, this is 5.4. E to the x was one of our favorite derivatives because the derivative of e to the x is just e to the x. Of course, we're not going to just give you a problem that says y equals e to the x and have you take the derivative. We're going to give you something that involves a chain rule, product rule, something along those lines. So if u is our exponent instead of x, u is some kind of a function, its derivative is going to be e to the u, right? Because e to the, and then keep whatever your exponent is safe, and then multiply times u prime. If u prime is just like a coefficient, you probably want to write it out front. So often you're going to write it with the u prime first and then times e to the u. I like that. Okay, choices on how you want to write it, but be familiar that you can switch around factors. Number 33 from your assignment was y equals e to the 2x power. That's e to the u. So y prime, the derivative is going to be e to the 2x times the derivative of 2x, which is 2. I'm going to put that in the front. Done. That's all you have to do if it's just e to the, and then it's an easy exponent. 41, you're going to have to use a product rule because we have x cubed as one factor, one piece, and then e to the x is the other factor. So how we did this back in the day is say like u equals x cubed and v equals e to the x. U times v goes to uv plus uv. First one's prime, last one's prime, right? U prime v plus uv prime. So y prime is going to be derivative of x cubed, which is 3x squared, times keep e to the x, plus keep the x squared this time, x cubed, times, and then take the derivative of e to the x, which is e to the x. Of course, this is a perfectly valid answer, but sometimes you are asked to do extra stuff along with it. Notice that both of these terms have an e to the x, so a lot of times multiple choice will factor out that e to the x. This is e to the x times 3x squared plus x cubed. Okay, that's a possibility. It's also possible that you might notice that x squared shows up in both of these, right? We got x squared and x cubed, but x squared is technically the greatest common factor along with the e to the x. So it's possible that they would have taken out like an x squared, e to the x, and left 3 plus x inside the set of parentheses. So any of these answers is totally valid on free response. Choices. This last example, I know there was one like this when I did the quiz back in December. There were plenty of multiple choice opportunities for you to practice this on the review that I gave. Lots and lots of multiple choice. So y equals e to the x to the fifth. So there's a whole bunch of junk going on here. Mainly our focus needs to be, how do we change this to look like e to the u? So this has got to be reworked. So it's y equals e to the u power instead of all of that extra stuff. So that means that this whole thing right here has to be u. let's do some side work. So u equals e to the x to the fifth. If we take the derivative of that, u prime, that's going to equal, keep the whole thing, right? E to the x to the fifth, we're going to keep it, multiplied times the derivative of its exponent. The derivative of x to the fifth is 5x to the fourth. Okay, so we know what u and u prime are supposed to be. Y prime is, you can put the u prime first or last, it doesn't really matter. I'm going to put e to the u times u prime. This is literally just the rule rewritten. And now let's substitute in. Y prime equals e to the u. U is e to the x to the fifth. Times u prime. U prime's at like the same level as e. So like just on that line, not above like an exponent, right? So u prime is 5x to the fourth times e to the x to the fifth power. Similar stuff to things we've done on other problems is noticing when things are common. We have I want to say denominator, that's not the right word, the base. The base of this exponent is e. The base of this exponent is e as well. If you have the same base that is multiplied times the same base, you can add their exponents together. Okay? I'm making this up right now, but if we had like x squared times x cubed, that's the same thing as x to the 2 plus 3 is 5, right? Basic algebra property. Okay, we're going to apply that, but the base is e. I'm going to start by rewriting the 5x to the fourth, because that's the easy part, times e to the. Now we will add our exponents together. They are not like terms, right? E to the x to the fifth is not a like term with x to the fifth, so we'll just rewrite them next to each other. E to the x to the fifth plus x to the fifth. Okay. Either of these is a completely valid answer. I just want you to be familiar with this for multiple choice situations. 8.7, L'Hopital's rule. L'Hopital's rule comes into play when we have a limit that gives us indeterminate form. Indeterminate form is something like infinity over infinity, 0 over 0, 0 over infinity, infinity over 0, 0 times infinity, 0 to the infinity power. Anything where you got like that weird mixture of zeros and infinities, indeterminate forms showing up. So what L'Hopital's rule says is that we're going to take that fraction that we've got and take the derivative of the top of the fraction and the bottom of the fraction. That way we don't have to do a bunch of algebraic canceling, multiplying top and bottom by conjugates, just all that messy stuff we're not going to have to deal with. We know how to take some derivatives, so let's put that into practice. Okay, first thing you have to do is show that the numerator and denominator both get you zeros or both get you infinities or something like that. And when I say infinity, it could be positive, it could be negative, either way. So let's start by plugging in infinity. Infinity is not a number. We're not actually plugging it in. What we're looking for is what is happening here. Is this getting really big? Is it getting really small? What's going on? Is it going really positive, really negative, or is it getting close to a number? Okay. So if we plug in infinity here, it's like plugging in a really, really large number, like, I don't know, a million or something. And then we'll plug in a million here, and then we'll subtract 1, right? So if we get a million squared, that's like what? 3, 6, 9, 12 zeros with a 5 in front of it. This is 6 zeros with a 3. Oh my gosh, numbers. 6 zeros with a 3 in front of it, and that's just subtracting 1. So if we have 5 and then 12 zeros, and then we subtract 3 million, that's barely going to put a drop in the bucket. We don't really care if we lose $3 million if we have like trillions of dollars. Yeah, trillions, right? So 5 trillion minus 3 million, nobody cares about this. Minus 1, nobody cares about this. So this 5 trillion is a super giant number. And as we start plugging in numbers that are bigger than a million for X, like a billion, this gets bigger and bigger and bigger and never stops. So this is infinity. Over. Same deal happens on the bottom. Plug in really big numbers. You get really big numbers as your answer. This is infinity over infinity. Now, of course, we know that fractions and limits cannot actually equal infinity over infinity. So you put that does not equal bit right there. Okay, let's keep going. We're going to use L'Hopital's rule now, putting the LH above that equal sign to show that's the step that we're taking. Otherwise, you got to write out the whole thing or an explanation or something. Show that work. Okay. We will take the derivative of the numerator and denominator, so that's 10x minus 3 and just 8x. If we plug in infinity again, plugging in supergiant numbers, multiplying them by 10 makes them supergiant numbers. We don't ever like settle on a specific y value. We just keep getting bigger and bigger and bigger, and same thing for that denominator. So this is infinity over infinity again. Boo. Okay, so since we still have indeterminate form, we're going to do this again. It's totally possible that you could have to do that 3 times. Probably not going to do that to you. Once or twice is absolutely enough in most problems. Derivative of the top and the bottom gets us 10 and 8. And now anywhere you see an x, plug in infinity. Trick question. There's no x's anymore. So you can't plug in infinity. The limit of a constant is that constant. So this equals 10 over 8, which reduces to 1.25. So as we go super far to the right while tracing this function, the y values get really, really close to 1.25. This is also called right end behavior. What is the right end behavior of this function? If this was a negative infinity, we would be looking for left end behavior. If this was a number instead, we would be looking at as x approaches from the left and the right side of, 4 or something, what are the y values getting really close to? This being an infinity is end behavior. That means that y equals 1.25 is a horizontal asymptote. That's neat. So the limit and the horizontal asymptote are the same thing. Woo, super exciting. I think that's the only one we really did in that section. So let's move on to 3.4, which was from January. The whole deal about 3.4 is the second derivative test and concavity. The second derivative test, using its name, you have to take 2 derivatives of your function. So we're looking for f double prime. F double prime tells us the concavity of f. Concavity is whether our graph is facing up or our graph is facing down, the graph of f. So if the second derivative is positive, your graph is concave up. If your second derivative is negative, your graph is concave down. Now, why do we care about this? Because we are told that we are trying to find mins and maxes. Well, take a look here. If you are concave up, right here is going to be a minimum. So we just have to figure out what is that critical number where we have, so a critical number, and we know that our graph is concave up. We have to figure that out. And we have to figure out for a maximum, where is there a critical number where f double prime is negative. So here's what we're going to do. We're going to find critical numbers from the first derivative. Basically, take a derivative, set it equal to 0, and solve for x. Then we're going to take all of those numbers, however many there are, plug them into the second derivative, and that's going to figure out whether our concavity is concave up or concave down, just like we talked about here. And if your graph is concave down or concave up, you can figure out based on the picture whether it's a max or a min. All right, if you get 0, it's not that there's no min or max there, it's IDK. We can't use the second derivative test. Just like, I don't know, we have to try something else. We don't have enough information yet. All right, here's number 34. Here's the original function. I went ahead and took those derivatives. We've done power rule enough. Okay, step 1, find the critical numbers from the first derivative. So we're going to set this guy equal to 0. We got negative 3x squared plus 14x minus 15. Since this is a quadratic, you can use the quadratic formula. Go algebra 1 style on this. If you don't want to use quadratic formula, you can try factoring. I would recommend multiplying both sides by -1, which will change the first sign to be a positive number. Or you can add / subtract everything over to the left side. It doesn't really matter. So choices there. We just want the first guy to be positive. And then let's factor. You can use the AC method. You can use box method factoring. You got lots of choices. The fact that 3 is prime means that this is 3x and this is x. 15 is either 1 and 15 or 3 and 5. They're both negative. So if this is a 3 and this is a 5, I think that works. 3 times 1. Yep, 3 times -3 is -9. -5 times 1 is -5. Add those together. Yep, there it is. Okay, since those equal 0, we're going to set each one of those equal to 0 and solve. We get x equals 3 and x equals positive 5/3. These guys are called our critical numbers because they came from the first derivative. Critical numbers are possible mins and maxes. Possible relative mins and maxes. So relative to all the points that are nearby these x values, are these taller or shorter than everything around them? Okay, we're going to test both of these numbers in f double prime. So f double prime of 5/3 equals, if we plug 5/3 in here, 6 divided by 3 is 2, so that's -10 plus 14 is 4, which is positive. F double prime of 3 is -6 times 3, which is -18, plus 14, which is -4. When f double prime is positive, that means your graph is concave up. If f double prime is negative, your graph is concave down. Concave up means that your critical number, it would be like a little picture, a little snapshot of a very small portion of the graph of f. This point is that 5/3 as the x value. It's at the bottom of the curve. So that means that x equals 5/3 is where our relative minimum is. And since 3, that critical number, gives us the top of a curve, x equals 3 is where our relative max is. Now, if we're looking for the point, not just the x value, we have to plug that 5/3 and that 3 back into our original function to figure out what the y values are. I don't think I did that on that paper, so let's try it. I mean, you can try that in a calculator. You know how to do it. 5/3 comma what? And 3 comma what? This number, the y value, is the min or the max. And I think that was pretty much all that we talked about. Email me if you have any other questions or anything you want to see me do.